Okay, hi everybody. Welcome to the bioseparation and downstream processing class. This lecture we will focus on the precipitation. That's right. Precipitation is the process that would like to separate like solute that dissolve in solvent. For this case, we have only one phase, like liquid phase. But in the liquid phase, there are more than one component. Like in water there are some protein, there are some amino acids dissolved in water. For this case, if we would like to separate protein or amino acid out of the water, another one technique we call this precipitation. That's like precipitation, we would like to separate out solute from the mixture, from the liquid mixture. That's like the product is in solid form. This uh, this figure is the introduction about the precipitation, like, or the precipitation technique. Like for this case, we have like the mixture in the liquid phase, in the uh, liquid phase, and also, sorry, this is a mixture in a liquid phase. We call this sample. We have a sample with the liquid phase, and some solute dissolved sample, and then we add some precipitating agent. We add some chemical to this, and this chemical will react with some protein, amino acid, and then interaction, and then there are some protein amino acid separate out, aside from the liquid phase. Protein and amino acid separate out into the solid form. Right. So then and after the separation, we get two phase, like liquid and solid phase. The precipitate is solid phase, and supernatant is liquid phase. Right. In liquid phase, there are also some amount of solute dissolved in the solvent also. And then we use like the gravitational field or centrifugation or filter something to separate solid liquid for the next step. Study the principle of the precipitation. The precipitation technique is make solute insoluble. Make solute insoluble and then aggregates out of the solution. The first step, we add some precipitating agent and then it make insoluble. And then it forms the solid phase and separate out. Fluency, the precipitation is used in the commercial separation of protein. The advantage of the precipitation is that it's relatively inexpensive. It's cheap compared to the other technique, right? And it can be carried out with simple equipment, right? And only a simple equipment, okay, we can use to separate. Can be done continuously, that's right? Can be done continuously. Okay, that means, and we also get the protein at the solid phase or the product at solid phase. This means the stable form of the product can be stored in the long term solid. Okay. And also, since precipitation is quite tolerant of various impurity, including nucleic acid, lipid, it's used in many bioseparation processes. Because we use this in the initially of the process. Because in the mixture, after we separate cell out, separate like the debris out, in the liquid, there are many components in mixture. Right? There are some lipid, there are some nucleic acid, protein, amino acid. If we would like to get protein as product, we can use technique to precipitate the impurity out first for this. Okay. In the native state, the protein in aqueous milk gets so much structure that minimize the contact of the hydrophobic amino acid residue with the water solvent molecule. And also we maximize the contact of polar and charged residue with the water. This means the interaction between precipitating agent is dependent on the charge of the molecule, the hydrophilic property of the molecule, something like this. Okay. The major for acting to stabilize a protein or amino acid or bioproduct in its native state are hydrogen bonding. This may be van der Waals interaction and sulfophobic interaction. Okay, in mainly we talk about the mixture after the separate of solids out. We call this fermentation board after we separate solid out. And the next one is only liquid phase. In liquid phase, mostly in aqueous phase. Mostly the component is water. The fault line van der Waals hydrogen bond or sulfophobic tend to put the hydrophobic residue into the interior of the protein. and the polar and charged residue on the protein surface. Things like this. It shows you right the interaction that's like for the molecule of water might to the surface of protein molecule because the association with the molecule of water might be this protein molecule. So this can separate out protein. And also another technique, another parameter that affect precipitation is the size and the molecule size, the size of protein. It's also important parameter that's like especially like the important for the solubility. That's like solubility. That's like, this can happen when non-ionic polymer. This is the precipitating agent. That's why we add the non-ionic polymer as the precipitating agent. Add to the solution. This results in steric exclusion of protein molecule from the solution. That's right, from the solution. This is the protein molecule occupied or aggregated by molecule of non-ionic polymer. That's right. And also depend on the protein molecule in the form of solid sphere. The polymer molecule in the form of slot. The following show the equation for the solubility of protein. For this case, we assume right the polymer is slot form and protein is sphere. And we can express the relationship between the solubility and the size or something like that. We can express at log S, S is solubility equal to beta minus KCP. That's right. And K can correct from the equation. The solubility means the maximum amount of the protein or our product that can dissolve in solvent or can dissolve in solution at any temperature and pressure content. For this case, RS and R are the radius of protein solute and polymer. We know that the RS is the radius of protein solute is the sphere. RR is the radius of polymer rod is log. That's right. V bar is the partial specific volume of polymer. Cp is the amount of concentration of polymer added to the solution. Beta is constant that's obtained from the experiment. That's right. Experiment. Okay. For this case, we can calculate beta and K if you have right the experimental result, concentration of polymer that affect the concentration of protein. Concentration of protein in terms of solubility S. Okay. And molecular size of the phenomenon factor. Molecular size is also the factor in type of precipitation, affinity precipitation. That's right. When the affinity group or antibody of a specific biomolecule, we call this antigen. If we add this antibody or the affinity group to the solution, that's right, the antibody antigen interaction and then conform like multi-molecular complex and then precipitate out. That's right, precipitate out. Like this example, that we have right the interaction between antibody AB and antigen AG that get the alkyl molecule and then can separate out by solid form or precipitate out. And the charge also affect the solubility. We know that the protein have a charge. When dissolve protein in water, it's ionized, negative and positive charge. The net charge of a protein has a direct bearing up on the protein solubility. The charge can affect the solubility. That means solubility of the protein increase and its net charge increase. A result of greater than interaction with dipolar molecule. That means if the charge is increased, the net charge increase. That means the interaction between protein and molecule of water with the dipolar molecule can react. Interaction is better. That's why it's so soluble. That's why it's more soluble in water if the charge is increased. And another that's like the repulsive reaction between protein molecule, right? And also increase the solubility. That's right. Okay, for this case, a simple way to vary the charge on protein, we can vary the charge on protein by changing pH of the solution. That's right, by changing out of pH of the solution. The pH of the solution, that's right. The pH of the solution does produce or indicate protein has zero charge or zero net charge. We call this is PS is the isoelectric point or PI, or isoelectric PS or isoelectric point or PI. That means at this PS, the charge of the protein has zero, and this is indicate that the solubility of protein is minimal. That's right, is minimal for this case. At PI, solubility of protein is minimal value. That's it. Okay. This show you like the effect of charge. That's right. When you increase the PS, the charge will be reduced. That's right. The charge will be reduced. And also, it is the law of solubility in protein per liter of solution. Like this. When you increase PS or you reduce the charge, solubility will increase until some value of PS about 5.5. That's like 5.5. This is the minimum solubility. And then if we increase PS further, okay, the solubility will increase. This means this means the PI. PS at 5.5 is the PI or isoelectric PS. That's right. Okay. This is the I show you is the minimum solubility at PI. The nature of protein determined by many factors, like total number of ionized stable residue. That's like sodium chloride. We have two ionized, sodium and chloride, for example. The accessibility of the ionizable residue to the solvent, the dissociation constant, like we call it pKa value. pKa value. This is based on when you dissolve some product, some protein, some amino acid, it can ionize in 1, 2, or 3 or more than this charge molecule. That's not charge molecule. Like sodium chloride, we have two, sodium charge and chloride charge. Sodium positive and chloride is negative charge, for example. And also the another effect is pH of solution. That's right, pH of solution. That's right. Besides of the chemical makeup of the ionizable group, factors that can influence pH value are like the chemical nature of the nice boiling group. That's right. Temperature, chemical nature of the solvent, like dielectric constant, ionic strength of the solvent, something like this. It is the effect to the pH value. That's right. And the next effect that is a solvent. Solvent also affect the solubility of protein. So we can add some solvent to induce the aggregation of the protein, to separate out by precipitation. And solvent affect the solubility by the term of the hydrophobicity or ionic strength. Hydrophobicity is don't like water. Ionic strength. The study of monohydric alcohol have shown that the denaturing efficiency at following. The denaturing efficiency, methanol is lower, is ethanol, propanol, and butanol. That means in the alcohol with longer acute chain. Longer acute chain means the carbon atom is greater than, it's higher carbon atom. That's like butanol, propanol. This is the binding more efficiently to a polar group on the protein. Weakening intraprotein hydrophobic interaction and thus leading to denaturization. Butanol, propanol can denature the protein. For this case, the methanol is preferred to use as solvent to separate out the protein because it low denaturing the protein. For example, this is the length for denaturing efficiency. The denaturing efficiency for the protein is the highest for this is butanol. If you use butanol, it may be denature your protein. Degrade your protein. And another like ionic strength of solvent can have both solubilizing and precipitating effect. For the ionic strength effect, we have two cases. The first case is salting it. For salting, that means if you add some ionic strength or some chemical which can ionize, If this case is increase the solubility, we call like the something when we add it, solubility of protein or our product increase. Why another effect? If we add some solution or some solvent, it decrease the solubility. We call it the precipitating action. We call it salting out. That's right. Salting in increase solubility. Salting out decrease solubility. That's right. For the salting effect has been observed for several proteins, including the class of protein named homoglobin. These proteins are insoluble in absence of salt at the isoelectric point of pi. That's right. For this kind of protein, usually it cannot dissolve. That's right. It cannot dissolve in water, but if we have like salt add to the solution, that means we increase the ionic state. The solubility is increased. That's right. Solubility is increased. In contrast, a member of another class of protein, such as like albumin, that's right. This is very soluble in water, that's right, as well as in high concentration of salt. Okay. For this case, the solubilities of albumin and the albumin differ because the albumin have much higher dipole moment than albumin. That's right. For this case. Okay. Okay. The solubility of protein is also depend on the surface of the molecule. Depend on the region on protein surface may be hydrophobic because don't like water. That's right. If we check the surface, there are some and there are some chart or not. Is polar or non-polar. If it's non-polar, that means hydrophobic, don't like water. Or if the surface is uncharted hydrophilic, that means this uncharted is fever water or like water. Positive charge or negative charge, something like that. It depends on the surface of the protein. It depends on the charge. It depends on the kind of molecule in the surface. This, for example, amino acid. Amino acid is the small molecule or biomolecule that is basic function or the element of the protein. So protein can produce from the amino acid. That's right. Bonding by peptide bond to be a protein. Amino is the minimal, that's a small molecule. Amino includes, right, three function is amino group, NH2, and carboxylic group, CHO, and other side chain. That's right. The property, the charge, hydrophobic or hydrophilic, protein, polar or non-polar, is depend on the side chain of the amino acid. That's right. This is example of the essential amino acid like this. We call like the glycine. Glycine is a simple amino acid. That's right. Glycine is a simple amino acid. There is no side chain for glycine. That's right. There is no glycine. For example, there's also like this is the lysine. That's right. It's lysine also like the ammonia group. That's right. Ammonium group like this. And this also right. Yeah, no, okay. You can separate, right? We can classify amino acid in terms of hydrophobic, in terms of polar, or in terms of charge. For example, like if we talk about alanine, Al or A. Alanine, that's how we remember that the group of the amino acid we have at least two, amino group and carboxylic group. And the side chain for this is CH3, methyl group. For this case, okay, there is no charge, that's right, there is no charge because we cannot ionize because the side chain is CH3. For this hydrophobic, don't like water, non-polar, and no charge, that's right. Occurrence in protein is 7.8%. And another, like some hydrophilic, some like aspartate. Aspartate is the non-hydrophobic. That's why it's non-polar and negative, something like this. And for the polar molecule like leucine, that's right. This for example. Leucine is non-hydrophobic but polar, non-polar or polar molecule. Sorry, this is X mean. Okay. Sorry. Okay, this is for alanine, that's right. It means like it's hydrophobic. Okay, it's hydrophobic. The cross symbol is mean that's yes. That's right. It's no. It's yes. Okay. But that's okay. Sorry for this. We can group the kind of amino acid in this slide. This is okay. The first kind amino acid with very non-polar side chain. That's right. Non-polar side chain like alanine, phenylalanine, isoleucine, leucine, methionine, valine, something like this. For example, is valine. Valine is non-polar side chain because the side chain is in this molecule of side chain is non-polar. That's right. Okay, the side chain is this. That's right. This is the carboxylic group. That's an amino group. This is a side chain. This is a non-polar side chain, for example, right? Or valine. That's right. This valine. Right? Is it hydrophobic or non-polar because it is don't like water. That's right. Another example, right, is amino acid with modulate non-polar side chain. This is a very non-polar side chain, but it modulate non-polar side chain. For example, with tyrosine. Tyrosine we have right this is the non-polar side chain, and purine is on non-polar side chain. That's why this carboxylic group, amino group. That's right. Or the purine. You know the purine, where's purine? It's purine. That's right. This don't like water also. No charge. That's right. And also polar molecule, non-polar molecule is modulate polar. Modulate non-polar. And how about amino acid with polar or with polar? We call this polar moduli. Two group. That's an ethanol group. That's an OS group. Something like this. Polar is serine, threonine. That's serine. Serine. Serine is non-hydrophobic. That's in polar molecule. For example. Okay. The positive charge amino acid like histidine, lysine, arginine, the positive charge means the side chain are weak basic. That's fully protonate or partially protonate and histidine. That's fully protonate lysine, arginine, and in normal biological condition. pH around 7. For the negative charge, amino acid like asparagine, glutamic acid, that's why the side chain are carboxylic. That's normally deponate at pH 7. Charge amino acids are very polar. For this case, you can look at the chemical structure for each molecule by this. If you know molecule, you can know is polar or non-polar, like threonine. This polar molecule. This OS molecule. For example, this polar molecule. This can help you. This is non-polar molecule. Something like this. Okay. Technique in making the biomolecule insoluble. That means we would like to precipitate out from the liquid phase to be the solid phase. That means we would like to make it insoluble, not soluble. We can make by isoelectric precipitation. Because that isoelectric precipitation is the point that is minimum solubility or something else. We don't like something it because something it, if we add some agent, the solubility is increased, but for something else, we add agent, the solubility decrease. Or we can addition, that's why we can add of organic solvent, we can add on non-ionic polymer, add polyelectrolyte or affinity precipitation like this. For the first technique we'll talk that is the isoelectric precipitation. Isoelectric precipitation, that means we precipitate at isoelectric. Isoelectric point mean the pH at the protein solubility is minimum. At this pH we call pI. We call pI. For example, that's like we would like to precipitate milk like casein at pI 4.6. pI 4.6 mean pH equal to 4.6 make the milk protein is minimum solubility. And soy protein, soybean, something like this. Okay, for this case, we can precipitate by adjust the pH of protein surrounding the pi, that's the pi. And the protein at pi, this means there is no net charge. The charge is zero. This makes minimum solubility. For example, if you would like to precipitate amino acid alpha carboxylic acid, typically pKa 2.4, positive and negative 0.5, that's right, or alpha amino acid group, typically pKa between 9.6 but negative 0.5, that's right. Certain amino acid also have side chain that may be charged. And we can calculate pi like this. The pi is equal to a half of summation of pKa. It gives you an example of pKa value for each amino acid. Like for each amino acid. Some amino acids have 3, some amino acids have 2. Mostly we have at least 2. That's right, that we have at least 2 because amino acid can ionize in at least 2 molecules. It gives you an example of pi. Pi means pH at the minimum solubility of protein. For example, peptine, pepsin, pi is about 1. Egg albumin, 4.6. Serum albumin, 4.9, something like this. Hemoglobin is about 6.8. For example, lysozyme is about 11, something like this. This is the pi value. Please remember that pi means pH that make the solubility of protein at minimum value. Okay. If we consider the relationship by Henderson-Hasbit equation, that's right. If we ionize Sa to be hydrogen ion and A ion, then you can calculate pH in the relationship between concentration of ionized molecule and pH, pKa, like this. pKa plus log of concentration of deprotonate species divided by concentration of protonate species. That's right. This equation allows us to determine pH. That's right. Given the ionic condition of the surrounding, if pKa and the concentration are known, pH can be calculated. That's right. And also we can calculate the degree of protonation or deprotonation of functional group at a given pH. Okay, I will continue the next technique to make the precipitation for the next lecture. For this, I will stop for the lecture now.